This video is sponsored by CuriosityStream. Get access to my streaming video service, Nebula, when you sign up for CuriosityStream using the link in the description. We often refer to solar energy as the ultimate renewable energy. Strictly speaking, that's only true if you figured out how to periodically renew the sun. But don't worry, as we'll see today, it is possible. A few weeks back, we were discussing what happens if we can't leave Earth. If all of our hopes for interstellar colonization to build homes around new stars just turns out to be impractical or undesirable. I argue that while I very much hope for a future in which we journey out to the galaxy, that even if we were confined to our own solar system, or just our own world, that we still had a very bright future ahead. Indeed, somewhat ironically, that is very literal as our sun grows brighter every day, and a billion or so years down the road would be too bright for our world to keep its seas and sky. If nothing is done, Earth will be turned into a hot, airless world much like Mercury, and then as the sun grows old and expands, and Mercury is swallowed up, there's a chance that solar expansion into a red giant might consume Venus and even Earth itself. Older models of stars tend to assume that they grew cold and died out slowly, freezing planets, and indeed that would be Earth's fate if the sun didn't consume it. After that roughly billion-year-long epoch in which the sun had been an enormous red giant, and then had shed much of its matter and collapsed into a white dwarf, Earth might very well get resettled. But that white dwarf would be far too dim unless Earth was brought closer, and it would continue to grow dimmer as the eons rolled by. In speculation, both science and science fiction, it was often contemplated that we might find some way to refuel our own sun, and that's what we'll be discussing today. But it is important to understand that, much like running out of air in a space station or spacesuit, the first problem isn't actually running out of a substance, but generating an excess of another. Humans breathe oxygen and exhale carbon dioxide. The amount varies by the individual and activity, but think between a pound to a kilogram a day. But carbon dioxide is lethal to us at relatively low levels, so long before we run out of oxygen, we would be poisoned by our own CO2, though we often get around this by blowing air out that still has plenty of good oxygen in it, just to purge the CO2 building up. Same concept applies to our sun. It is burning through its fuel, hydrogen, but in the process it turns that into helium. It also contains plenty of other heavier elements made in the older dying stars that formed our solar system. Most of the elements heavier than hydrogen and helium, which are called metals in discussion of stars, are in our sun, not just our planets. They also positively affect a star's lifetime, actually extending it, whereas the buildup of helium shortens a star's lifetime, and today we'll discuss harvesting those for construction uses, but also as part of a process of extending our sun's lifetime almost indefinitely, and even other stars as well, including rekindling dead stars like white dwarfs, neutron stars, and even black holes. Now, this episode isn't going to be a deep dive on how stars fuse hydrogen into helium or into other final products, nor on how stars die, but the key point for today is that, when you have a high enough pressure and temperature, protons will slam into each other far more often, and with far more energy, and for a given collision energy they have a chance of sticking together in a way that turns the 3 quarks in each of those protons, 2 up quarks and 1 down quark, into a new big ball of 6 that has 3 quarks of each type rather than 4 up and 2 down. Most of the time this is not what happens. We get a diproton, which just falls back apart into 2 protons, but sometimes we do get that quark change. This is a proton and neutron now, or a deuteron, the atomic nucleus of a deuterium atom, an isotope of hydrogen. In our antimatter factories episode, we discussed more on how quarks work and how they can change like that. Deuterium running into another deuterium to form helium is often mistakenly thought to be the next step, since a pair of deuterons contains a pair of protons and neutrons, which is what helium is, but that's actually not the normal situation. Once a deuteron is made, there are 4 main fusion reactions that can occur with it inside your typical star. It can run into another proton and absorb it, and that is now helium-3, 2 protons and a neutron. Two of these can collide and produce a helium-4 atom, plus a pair of regular hydrogen nuclei, lone protons again. And we call this the proton-proton or the pp1 branch. Sometimes a pair of deuterons slamming together will make helium-3 plus a neutron, sometimes it will make tritium and a proton, or a hydrogen nuclei with one proton and two neutrons and another lone proton. Deuterium bouncing into tritium is very rare because tritium only lasts around a dozen years before decaying into helium-3, but it is a very easy fusion process into helium-4 plus a neutron, and is why we want it for controlled fusion here on Earth. A deuteron plus helium-3 can also produce a helium-4 atom plus a lone proton too. Key thing is that none of this ever happens from an observer standpoint. These particles are moving insanely fast in a very dense environment, so they are slamming into each other constantly and at high energy. But the odds of two protons colliding and forming a deuteron is less than 1 in many trillions when these collisions happen. The average proton will kick around the Sun's core for 9 billion years, colliding almost constantly with other protons and bigger nuclei before successfully completing Step 1 and merging with another proton to become a deuteron. A star with higher pressure and temperature is exponentially more likely to have this process occur, which is why a star only twice as massive as our own Sun will go red giant in less than 2 billion years, whilst a star that's half as massive as our Sun could live nearly 60 billion. It's also why you don't get stars much bigger than our own Sun, the way Jupiter is bigger than our planet. They couldn't even form before they would hit such a rate of fusion that they'd be torn apart by their own immense heat. This is a factor in why you often have a whole bunch of giant stars form near each other, and often a big star will burn itself out and explode before it could gain more mass, especially as it's blowing tons away as solar wind once ignited. This is also why a supernova, in mere seconds, can fuse more particles than our Sun will in its whole lifetime. A given particle is colliding many times per second. They are smushed together very tightly compared to normal matter and moving vastly faster. When the odds for fusion from those many collisions per second drop from 1 in a quintillion per second, like in our Sun, to just 1 a second, like in a supernova situation, things change. This is why we joke on the channel about controlled fusion not being about trying to replicate the fiery conditions in the heart of stars, but rather needing to go far beyond that, and we achieve something closer to that with a hydrogen bomb detonation. It's all about having an energy level in particle collisions high enough to make a fusion event likely. Core matter of our own Sun produces very little power. It would take several tons of it to run a light bulb, but there's an awful lot of sun, and those tons of matter will run that light bulb for eons. Fusion is millions of times denser in energy than an equal weight of chemical fuel like gasoline. Now, in a star, all these fusion events, rare as they are, make the star hotter, and heat can only escape from them by radiation, so the stars cool very slowly. Dead ones take eons to cool enough to not be glowing white hot anymore. In living ones, or stars on the main sequence, all that trapped heat makes the individual particles move very quickly and then they shove apart, while gravity holds them together, and the hotter it is, the more likely fusion is to occur, which would make them even hotter. But the hotter it is, the harder it is for gravity to hold it together and keep the core pressure high, so every star reaches a size and temperature that is stable, what we call hydrostatic equilibrium. Pressure and temperature are maintained by the rate of fusion and radiation, or sunlight given off. But it's not really stable. As time goes on, all the deuterons and helium-3 and helium-4 particles start getting more common. In a younger star, there's less helium, and helium is denser than hydrogen, so as fusion makes more of it, the star gets denser. The star's pressure is a function of that density and temperature, so it rises and the fusion rate rises with it. Thus, stars slowly get hotter as they age and thus brighter. Eventually, this tips them into being a subgiant, which can be several times brighter than the star was when it first ignited, and then it transforms into red giant phase, which can be many hundreds of times brighter than the original star. In truth, in these stars, what you really have is a small core and an enormous thin atmosphere, whereas the main sequence stars have relatively large cores. emphasis on relatively, as our Sun packs about a third of its mass into its core, but that's only about a fifth to a quarter of the Sun's width, about 1% of its volume. So a grape inside a grapefruit, small but still huge compared to a red giant, where the analogy of the core would be more like a shriveled up grape or raisin inside a beach ball, or even larger. All that beach ball region is too expanded out from the core to swap in new fuel, and the helium content is rising and making the core even denser, so it chokes the star off eventually as layers of the outer red giant are shoved out away into space, while that inner bit just shuts down into a big ball of helium in most stars, though bigger ones can go through another fusion cycle to make heavier elements. I mentioned earlier that the buildup of helium accelerates fusion and thus kills a star, but I also mentioned that other metals slow fusion down. Every star has a metallicity, and older stars that formed when the universe was young and with fewer metals have lower metallicity, which again in astronomy is anything which is not hydrogen, helium, or one of their isotopes. It is far harder to shove two bigger nuclei together to fuse into something yet larger, so it requires far more pressure and density and temperature to make that likely. So in a normal star, those as massive as our Sun or less, all those metals inside it just bounce around and their collisions produce nothing. A hydrogen isotope slamming into a bit of iron or neon is just going to bounce off. The more of those metals that are in there, the slower a star burns. It might seem strange then to try to remove those metals. Solar systems form from the same basic cloud, planet and star alike, and that means most of the metals and useful elements are in our Sun. It might seem crazy to think of removing those from a star, but as we'll see in a bit, it can be done. Now, a white dwarf is the final state of very nearly every star, but because most stars are less massive than our own Sun, and the universe hasn't lived long enough for those stars to die off yet, the ratio of bigger stellar remnants is higher, but 97% of all stars currently in our galaxy should end as white dwarfs. But again, we do have a fairly large percentage of neutron stars and black holes, just because the overwhelming majority of stars large enough to form either, having lifetimes much less than 1 billion years, have died already. Thus, we think we have about 10 billion white dwarfs, about 1 billion neutron stars, and about 100 million black holes in this galaxy. Those are estimates, but it makes us about 1% black holes, 10% neutron stars, and the rest white dwarfs currently, with dozens of times that as stars still in the main sequence or red giants. Over time, the white dwarfs will become more common, but they'll also slowly cool to being black dwarfs, ultra-dense balls of helium or carbon mostly. Now, this episode is really more about refueling our Sun so it never goes subgiant, let alone red giant and white dwarf, but let's talk about refueling these first. Giant stars exploding as supernovae is just one type of them, called Type 2, and these end as neutron stars or black holes. Type 1a are actually white dwarfs which sucked in new hydrogen off a binary partner and exploded. This is actually very common because stars often form as binaries, and those pairs are usually not the same mass. So one will go red giant first, the more massive of the pair, and often they're close enough that the other smaller star will end up orbiting inside that red giant or stealing mass off it. This can cause them to slow in their relative orbit from drag and mass exchange so that they're even closer. However, once that bigger star turns into a white dwarf, it will be the second star's turn to go red giant, and now that white dwarf is gaining hydrogen from the outer layer of the red giant. A white dwarf is essentially a star's core that runs out of fuel, so dropping hydrogen on it just causes fusion and it glows again. Big chunks of this can cause a regular nova. These are the far more common and less bright kind we see that are temporary new stars in the sky. There are usually several in our galaxy each year, typically in Sagittarius, which is where the galactic core is, and novae can happen repeatedly to the same star. But they are less bright, so we only see the ones in our own small corner of the galaxy, whereas supernovae are visible galaxy-wide. There were a few naked-eye visible ones in 2021, though barely visible. Some are much brighter, they last days to weeks, and recurring novae can be periodic. For example, if the binary twin in an orbit every decade, then a lobe of gas can get sucked away at that frequency. You can also get white dwarf pairs left behind that eventually spiral into each other. White dwarfs vary in mass, often around half that of the original star, but they can only be about half again as massive as our own sun before they hit a critical point and can now begin burning carbon, and that results in a rapid progress to supernova, and nothing is left behind by this, no neutron star or black hole. This results in a very specific and characteristic explosion, and one visible by telescopes billions of light years away, so we can very precisely determine the distance to a Type 1a supernova by measuring its brightness to us and the redshift of its various spectra. That's been instrumental in so much of our research into the size and nature of the early universe, Hubble expansion, and dark energy. But it's not the sort of thing you want to have happen in your backyard, and indeed your typical nova is a bit much and brief, so instead you would be manually feeding in hydrogen at a steady rate. You could potentially set this up in a binary system with sufficient megastructures, but you could trickle feed our own sun Jupiter for many millions of years of good light. And if its white dwarf version was about half its current mass, it should be able to take 1,000 Jupiters before exploding. However, this is not sunlight. Indeed, we have objects called super soft X-ray sources that emit low energy X-rays, between 90 to 2500 electron volts, where red photons are about 2 electron volts or EV, and blue light is about 3. UV or ultraviolet runs from 3 to 30 EV, and then you get into the X-ray range. Hard X-rays are about 1000 to 20,000 EV. Beyond that you get into gamma rays. We believe these soft X-ray sources are from white dwarfs and produced by steady nuclear fusion on a white dwarf from a small but constant matter injection from a companion. They are still enormously bright, the dimmer ones are 100 times brighter than our sun, but a shell constructed around one which could absorb the X-rays and emit them as safe visible light could run a Dyson swarm 100 to even 10,000 times as large as one made around our modern sun could support, whereas the typical white dwarf is hundreds or even thousands of times less bright than our sun. You should be able to import hydrogen to a white dwarf though, and with sufficient effort keep it fed and modified to mimic the original star it came from, and for a period of time longer than it originally lived on the main sequence. Everything landing on it is fusing after all, whereas most stars don't fuse all their mass. That mass, the Chandrasekhar limit, where they explode, is slightly higher if the star is spinning very rapidly. Dead stars typically do too. Pulsar neutron stars can spin in seconds or less, rather than days or months like many planets and stars do. It should be a bit higher if the white dwarf has cooled a lot too, so a civilization reigniting a white dwarf this way probably could push that limit out a bit by a mix of patience and dropping the matter to maximize angular momentum, speeding the dwarf's spin rate up. Eventually though, your star is going to reach that maximum mass, and you would then have a ton of time while a white dwarf that massive cooled, but you are done, and anything more will blow it up, possibly excluding the careful dropping of a micro black hole into it. Neutron stars would follow a similar path, though adding mass to them not only eventually would push them into being a black hole, but could cause a star quake, which can result in a gamma ray burst good enough to wreck the ecosystems on worlds around neighboring stars several light years away. Again, not something to play around with in colonized areas of the galaxy. Ironically, black holes are the safest thing to feed. You just pick a material that can absorb gamma and X-rays well and has a melting point hot enough to glow in the visible light range, like tungsten, and put that as a spherical shell around that black hole, then dump matter down into it at a rate which you want. The accretion disk that forms will give up energy at a rate far more efficient than normal stellar fusion, and thus let you extend the star's lifetime even more. Indeed, you could trickle feed a white dwarf into a black hole and get positive energy out of it. There's all sorts of ways to use black holes for power this way, including creating a micro black hole whose radius was exactly the right size to let you dump it into a gas giant and have it suck in matter at a sustained rate, heating that gas giant up, and probably producing secondary fusion near the black hole too. Black holes don't really gobble things up the way sci-fi tends to indicate. see our episodes Making Stars or Colonizing Black Holes for more on these options. And they are neat options for reviving dead stars, but let's get to keeping our sun alive. First, as we discussed in greater detail on our episode Starlifting, it is possible to remove matter from a star. Indeed, they naturally push matter off them all the time. That's what solar wind is and what flares and coronal mass ejections, or CMEs, are. If we heat a spot on the sun up, it will tend to erupt out with a spray of hot plasma. Now, the upper layers of the sun are not thick. Do not think of these eruptions as magma-like blasts. The photosphere of a star is incredibly thinner than air. That photosphere is what we usually think of as a star's surface because it's the layer the light we see comes from. Light particles created below it usually will pass through enough matter to be absorbed by it and re-emitted at a new frequency as a new photon. The photosphere is where we are far enough out from the sun that things have thinned down and there's not much left above, so a photon passing through can often get away without being absorbed and reach our eyeball millions of kilometers away. The temperature of the photosphere therefore controls what frequency of light we see. The core itself emits light in gamma and X-ray ranges, just like those naked or collapsed degenerate cores we see with white dwarfs and neutron stars, or the accretion disks of black holes. That photosphere is about 100 kilometers thick and is made up of giant convective cells of plasma we call granules that move at around 7 kilometers per second and usually last about 20 minutes. Think of these as boiling bubbles in a pot of water. If we heat these up more, they will blow matter off into the solar system that we can capture. Everything coming off the sun is ionized plasma of ions and electrons, so shoving them out magnetically is an option that works well. Now, folks tend to assume all the heavier elements collect in the center of stars, and the onion model we show of supernovae doesn't help with that, where you have layers of ever heavier elements, but that's not really how it works and why the bubbling pot analogy is more apt. Bigger atoms are denser and thus do tend to slowly sink, but the whole thing is highly mobile and thus the photosphere of our sun is 74.9% hydrogen, 23.8% helium, and the remaining 1.3% is other metals, with oxygen, carbon, neon, and iron making up most of that, and in that order. Mining those out is just a matter of blowing them out, and we detailed how in our starlifting episode, but the key ways are either to shove it off magnetically or by superheating spots on the sun, or some combination thereof. One of the methods involves making mini rings or satellites around the star, made of stations that you can lift or drop to let us expand and contract each ring, which creates a big magnetic shove below, then do them in a sequence as a way to force matter to be squeezed off at the north and south pole, then caught somewhere above by a mixture of magnetic vacuum cleaner, reverse ion drive, stellar windmill, and statite. Your rings then use solar power to shove magnetically back up in altitude for another drop, creating an accordion-like pumping action. This method pushes out the poles rather than into the orbiting plane of planets and an emerging Dyson swarm, and this can all be powered by the sun's own illumination and requires no special new science or super materials, just massive effort, and it's the sort of thing a civilization does when it's already disassembled all its asteroids and smaller moons and is trying to decide if they need to disassemble planets for construction materials. The sun has more mass than all those planets and metals, so it becomes an attractive option. But more relevant, it's a civilization that already has a massive presence in space and has climbed a long way up the Kardashev scale, so building big ring stations around your own sun is not some Leviathan task. It's probably comparable to building a highway system for them, and it's how they get mass to build more civilization. This might be something we're contemplating in even a few thousand years, but for all purposes today it would be okay if we waited several million, because the key thing is that while it is nice for removing metals for fun and profit, you are also removing tons of hydrogen and helium too. And you can just drop that hydrogen back in if you want, but keep the helium. Indeed, lowering any star's mass is going to lengthen its lifetime, but by pulling the helium out of the photosphere constantly, as it mixes with lower layers and seethes around, we can decrease the overall helium content. This is step 1 to lengthen the sun's lifetime, because we're removing the poison of helium, which speeds fusion up and heats a star. And in doing so, we'd actually make the sun a bit dimmer by lowering its mass too. We get about 600 megatons of hydrogen turned into helium, neutrinos, and sunlight by the sun every second, and virtually all of that mass is helium. So while removing any at all would help extend the sun's life, to keep up with things, we want to remove 600 megatons per second. Again, we're not refueling the sun yet, just removing things which will kill it quicker. The sun masses 2 billion trillion megatons, about 3/4 of which is hydrogen currently. It had a lot to begin with incidentally, but that represents about 75 billion years of remaining burning if that was all used and at a steady rate, not the 5 billion or so we have before the red giant phase would naturally occur. Again, we haven't done anything to refuel the sun yet, just removed helium, and we've extended its lifespan many times over by doing this. Technically, we are dumping a lot of hydrogen back in, since most of our star lifting will be hydrogen, but this is more like a solar fountain off the poles that we're filtering, not refilling from. Which brings up a good question of what we're doing with all that helium. 600 megatons, or a bit less, every single second. It is not a horrible propellant for spaceships. You could run some very impressive shipping by directing external power beams into helium tanks that spew them out the back of a ship at 1,000,000 degrees. See our episode from a couple weeks back about owning your own personal spaceship for more discussion of that. Helium makes a decent radiation shield too, if you want to cram it into hollow tanks on the outside of spaceships and space stations, and you could dump it down into a black hole for more power if you got that technology. I generally assume that if it is possible and practical to make artificial black holes, then you have figured out how by several million years from now, so it should not be out of our thoughts for contemplating how civilizations power themselves. Incidentally, Jupiter is 73% hydrogen and 24% helium, very similar to what our Sun is and what Saturn is, which is what I meant about our Sun starting off with a lot of helium in the first place. I think folks hear the amount of sun that's helium and assume that it's being nearly a quarter helium is why it's halfway through its life, but no, it inherited almost all of that from previous dead stars and the Big Bang. Jupiter contains about 75 million years worth of new hydrogen fuel for the Sun, Saturn about 25 million, and Uranus and Neptune a few million each. Small potatoes compared to the Sun's normal lifetime, let alone its extended helium-filtered life, but keep in mind just how long 1,000,000 years really is for a civilization. Even the smallest of all gas giants would be buying us an extension of life hundreds of times longer than our entire recorded history. Speaking of that, when we've discussed colonizing giant stars, I point out that even though those measure their lives in millions, not billions of years, that it still made them logical to colonize. It's occasionally suggested we would colonize everything but these immense and short-lived stars, and I argued in that episode that quite to the contrary, these megasystems, which might have hundreds of planets and be able to support a Dyson swarm 1,000 times bigger than what our Sun could, might be the great empires of future humanity. Those stars simply have so much more power output and so much more mass. They are also way easier to starlift off of, as the bigger ones are already gushing off planets worth of matter from their sheer immense internal fusion and heat, so it is not too hard to mine them and to helium filter them too, especially as you lower their mass. Well, what to do with that lower mass? For our Sun, as we poured off all that plasma, we sorted it and dumped the hydrogen back. That's an easy sort too, because a magnetic field will act a bit like a prism does on light for ionized matter of different masses, breaking things up by element on large distances. A matter rainbow, so to speak. In these other suns, though, fated to short lives, we can massively extend their lifetimes by not dropping all the hydrogen back in. And while I think most systems would prefer to keep their excess hydrogen around for long-term use, I would imagine they would sell a lot of it, and I would also imagine that Earth and our Sun would be in a very good position to stockpile at least several thousand solar masses worth of hydrogen from the hundreds of billions of them spread throughout the galaxy. Drop in the bucket, bought by the planet and solar system that's likely to be the richest and most technologically advanced system in that galaxy for many millennia to come. Presumably you store that as a big planet size or even brown dwarf size gas stockpiles. Saturn-sized ones are a nice compromise spot, as a planet composed of hydrogen of Saturn's mass and size could have a shell wrapped around it to further minimize leakage of hydrogen, which would have a surface gravity similar to Earth's. Shell worlds, or super-mundane worlds of this size, do not really need active support because the hydrogen side, or helium for that matter, would prop the shell up the way gas in a soccer or basketball keeps them rigid. You build them about as far from the sun as Earth is, then you cover them with dirt and air and water and call it a planet, one with around 100 times the living area of Earth, and containing enough fuel for the sun to run itself for 25 million years. Incidentally, the sun produces enough sunlight to light up 2 billion Earths or 20 million of these Saturn shells, so hypothetically, you could have 500 trillion years worth of fuel stored in them, and you could be replenishing their hydrogen with helium to keep the mass right as you tap them. I think you would probably not go that route since it would spike the solar system's total mass up 6,000-fold, which definitely does some strange things to orbital periods, plus making a Dyson swarm of actual planets is not a good plan. You could do mini Kepler rosettes of planets and rings around the sun, and each one further out and maybe has lighted beams in by statite mirrors above the sun. Done right, the increase of mass of each ring can let you keep the ring past it at the same year length, as more mass in the center to orbit around makes orbits faster. Done really right, you could keep each ring orbiting with the same year length and fixed relative position, and build giant bridges between them, but that's a whole different topic for a whole different episode. But you could have many thousands of them near the sun and many more far out in the Oort cloud, maybe getting power beamed out to them, or just running on fusion reactors. A big star pump for moving helium is a great way to grab deuterium too. And while there's still room to doubt if we'll ever get commercial fusion reactors working, you should be able to at least make a planet-sized deuterium fusion reactor work. If we do have artificial fusion, one might ask why bother doing this extension on our own sun, and more so if we had artificial black holes. The latter is trickier to argue, but that's also much harder technology, and stars are likely to be the cheapest fusion power systems. It's a process where letting raw mass do the work is likely to result in the minimum maintenance and cost. It is possible we might never colonize beyond this solar system, though it is hard to imagine we could engage in starlifting but not star travel. We discussed a few weeks back why we might be able but unwilling to leave Earth in our system, but we might send out robot collectors even then. So too, our sun is not stationary. It orbits through a giant sea of galactic dust and gas, and we could harvest a lot of that as we spiral around by setting up collectors out past the heliopause. It's not even a light day away. We already have sent spacecraft that far, Voyager 1 and 2 both got there functioning, so we should be able to do it again, and it may be feasible to collect ionized stellar gas and bring it home to our own sun. I don't think we should rule that option out, or for that matter other higher tech ones like opening a wormhole from our sun to empty space to clear out core matter and replace it with hydrogen, or even weirder options like opening a gateway to a younger universe as an infinite supply of hydrogen. More importantly though, Earth is always going to be our first planet, and our sun, Sol, our first star. And it wouldn't be like the hypothetical birthplace of mankind where we only know in modern times where our first tribe might have come from. We'll never forget Earth and the sun, so it is easy to imagine extreme efforts being taken to preserve them for as long as possible. Our first sun could then easily end up being our last sun too, as others were disassembled or died, but Sol remained, rising every morning for untold trillions of days to come to give life to our world, as it has for so many days before. So we were talking a lot about fusion today, in stars and hopefully in power plants in the future. If you want an update on how progress is going and what the challenges are on fusion, there's a great episode of Engineering the Future on Fusion over on Curiosity Stream. Also, when I was working on this episode's video portion, I ended up subtitling it Holding Back Eternity because it seemed like that was the main motive for Refueling Our Sun specifically, and I thought we'd take a few minutes to run the numbers on how long we could do that in an extended edition of our episode over on Nebula. Nebula, which is now the largest creator-owned streaming service, was started by a handful of us as a way to give creators more options for their work, and a platform designed for creators and their audiences, not ads, and every new episode of SFIA comes out there a few days earlier and without ads or sponsor reads. We also have an audio-only version of our show available there too, early and ad-free as a podcast, as well as all of our extended editions like we'll be having today, and some Nebula exclusives like Plants vs. Megastructures and the Coexistence with Aliens series. Nebula is a great way to help support some of your favorite channels while getting ad-free content and bonus material. Now, you can subscribe to Nebula all by itself, but we've also partnered up with CuriosityStream, the home of thousands of great educational videos like Engineering the Future, Fusion. That lets us offer Nebula for free as a bonus if you sign up for CuriosityStream using the link in our episode's description. Again, you can get CuriosityStream and Nebula for less than $15 a year. Just use the link in the episode's description. So these kind of insane mega projects require efforts that are mind-boggling, but they get a bit more believable when you have superior automation, and next week we're going back to the near future to look at what automated economies will look like in this next century, and also discuss worries about unemployment in those emerging economies. That will be a somewhat serious topic, so we'll go from that to our Sci-Fi Sunday episode, Stranded on an Alien World, to lighten the mood and contemplate how we would survive if left on one, and we'll follow 4 stories of people stranded on everything from places much like Earth towards deader than the most barren desert. And 2 weeks from now, we'll contemplate the exact opposite of a dead world, a world which was alive itself, as we discuss the Gaia Hypothesis theory. If you want alerts when those and other episodes come out, don't forget to subscribe to the channel and hit the notifications bell. And if you enjoyed today's episode and would like to help support future episodes, please visit our website isaacarthur.net for ways to donate, or become a show patron over at Patreon. Those and other options, like our awesome social media forums for discussing futuristic concepts, can be found in the links in the description. Until next time, thanks for watching and have a great week.